While the special theory of relativity dealt with a given frame of reference that was at rest or moving at a constant velocity, Einstein's general theory of relativity tackled the problem of accelerating reference frames. Of the four fundamental forces, gravity is usually the most well known. Gravity separates itself from the strong, weak, and electromagnetic forces in a couple very distinct ways. First, gravity acts over long distances, astronomical distances even. The strong and weak nuclear forces only act on the order of the size of a nucleus. Electromagnetic forces can act over long distances, but they can either be attractive or repulsive, which is the second difference in gravity. It is only an attractive force. Gravity is the attractive force between two masses. Since there is a lot of large mass accumulations in the universe, gravity can act over very long distances. In his special theory of relativity, Einstein showed that the speed of light in a vacuum did not depend on the motion of any observers. He also supported the idea that the laws of physics were the same for anything that was not accelerating. The conclusion to this is that there is no way for an observer to determine whether a given frame of reference is moving at a constant velocity or not moving at all. Not long after publishing his special theory of relativity, did he start to determine whether or not the laws of physics are consistent in an accelerating frame of reference. Einstein spent a good decade trying to include acceleration in his special relativity, but in the end, he published his general relativity by developing a new theory of gravity. As a thought experiment, consider a person in a free-falling elevator. If that person lets go of a ball, what would happen? Gravity is pulling down on the ball, but it is also pulling down on the person at the same rate. So the ball would just hover right there along with our person. We can even verify this would happen when we look at astronauts and all their stuff when they are in orbit. The thing is, this effect on the ball is exactly the same as if this reference frame was at rest and there were no forces acting on it. It is also the same as if the ball were in space where the gravitational field is essentially zero. These two descriptions are equivalent to each other. Now let's put our elevator in space and accelerate it upwards at a rate of 9.8 meters per second squared. The ball, as seen by our observer, would fall to the floor, just as if it were falling due to gravity at the surface of the Earth. Again, these two descriptions are equivalent. Based on these observations, we can conclude that an observer in an accelerating elevator in deep space observes the same thing as an observer at rest on Earth. The two observers cannot tell whether they are at rest in a gravitational field or accelerating in deep space. Einstein extended these observations into his principle of equivalence, which says that observers cannot distinguish between a uniform gravitational field and an equivalent uniform acceleration. Isaac Newton was the first to really describe gravity in his universal law of gravitation. Remember, this law states that every particle is attracted to every other particle. The strength of the attraction increases as the particles come closer, and also when the masses are larger. So gravitational mass refers to how much something weighs in a gravitational field. But remember, he also defined mass in terms of its inertia. Inertial mass is the amount of force it takes to get a mass moving. No experiment that we have ever done has shown a difference between inertial mass and gravitational mass. So really, this is just another way to state the equivalence principle. Gravitational mass is equivalent to inertial mass. In other words, the effect of gravity and the effects of acceleration are equivalent. Einstein really didn't like that two different theories defined one thing. He felt that there should be one explanation for both gravity and acceleration. One interesting idea to come out of this principle of equivalence is that light ought to be deflected by a gravitational force. Say you're in an elevator at rest or moving at a constant velocity. You shine a flashlight onto the wall, and the light travels across the elevator and strikes the wall at some initial height. Then the elevator is accelerated upwards. During the time that it takes the light to travel across the elevator has moved upwards at a vertical speed that is increasing relative to the light. As a result, the light hits the wall of the elevator at a point below the original point when the elevator was at rest. In fact, the light has to travel in a parabolic path similar to that of an object in projectile motion. According to the principle of equivalence, a beam of light in a gravitational field must also bend downwards, just as it does in an accelerating elevator. Now, obviously, we don't notice this phenomenon on Earth, since Earth really isn't that big, and we are talking about very small distances. For reference, light traveling near the surface of the Earth for a distance of 1 kilometer is deflected only about 10 to the negative 10th meters, or about the width of an atom. Calculations show light from a star passing by the sun, however, would be deflected by 1.75 arc minutes. Still small, but detectable. Because of the brightness of the sun, experiments taking such measurements can only be done during a total solar eclipse. And actually, one such experiment was carried out in 1919 by Sir Arthur Eddington. Obviously, you can't really see this picture, but his results confirmed Einstein's predictions. The more powerful the gravitational force a body has, the more it can bend light. And some of the results are simply amazing. In this Hubble Space Telescope picture of the Cheshire Cat group of galaxies, the mass that distorts the faraway galactic light is found surrounding the two giant eye galaxies and a nose galaxy. The multiple arcs of the circular face arise from gravitational lensing of 4 different background galaxies, well behind the eye galaxies. This is where Einstein came up with the idea of the space-time fabric. It has long been thought that light will travel the shortest path between 2 points. So if the path of light can be curved, then so can space itself. So did you know there was more than one kind of geometry? The geometry that you learned in high school is what we refer to as Euclidean geometry. Parallel lines do not intersect. The 3 angles of a triangle all add up to 180 degrees. That's Euclidean geometry. This is our normal way of viewing the world and what we take as fact to explain the things around us. But when we are talking about a curved space, we need to use the concepts spelled out in non-Euclidean geometries. So let's try to imagine this. In regular geometry, when you draw a triangle, you are drawing it in a 2-dimensional plane. If you were to add up the measurements of all 3 angles, you would find their sum to be 180 degrees. But if you draw the same triangle onto a space that is curved and add up the measurements of all the angles, the sum will not be 180 degrees. This is clearly not a Euclidean space. Within Einstein's concept of space-time is the theory that matter and energy distort space, and that distorted space affects the motion of matter and energy. In other words, space itself can be curved, and it is gravitational mass that causes the curvature. An often used visualization of the curvature of space-time is a bowling ball on a trampoline. When you add the large mass to the fabric, the ball sinks down and the fabric curves around it. Smaller objects put in motion around it will be pulled in. This gives us a nice way to visualize space-time, but keep in mind that there are quite a few actual limitations to the model. Plus, if we really want to get into the nitty-gritty details, we need to visualize it in 4 dimensions, not just 2.